Good morning, class. We are talking about real population growth today. Real population growth is important in our world, and probably the most important thing that we deal with is human population and what's happening with human population and human growth. And the formulas that we learned in 8B will be applied a lot of times to the formula or to the problems that we're dealing with in 8C. So perhaps the most important application of exponential growth concerns human population. So from the time of the earliest humans, more than 2 million years ago is what they think, until about 10,000 years ago, human population probably never exceeded 10 million people. But then there was an advent of agriculture, and then it brought about more rapid population growth, and things just really took off. So if you look at this little graph that's on the screen, and you also have a picture of it in your notes, that's human population growth right there. So you note that everything was fairly stable for a long time, and then right there is where that agriculture, the advent of agriculture happened, and then all of a sudden things just really took off. So human population is estimated to have reached about 250 million by 1 AD, and then it continued growing slowly till about 500 million by 1650. And that 1650 is about right there where things barely started. So consider the following. There's just a bit of information for you about population growth. Every 4 years, the world adds nearly as many people as the total population of the United States. So that happens about every 4 years. And the population is around 327 million, but that's how much is added each year, each 4 years. Each month, world population increases by nearly the equivalent of the population of Switzerland. And then also, while you're studying, during the next hour and a half, the world population will increase by about 10,000 people. So there will be 10,000 people born above the amount who die over the next hour and a half, if you count everybody across the entire world. So this is pretty cool. You notice that this is exponential growth. Hopefully you notice that it's growing so rapidly. And it might be a bit that we're dealing in billions of people here. So it's we've got 1 billion, 2 billion, 3 billion on the units for the vertical axis, and then time, as you see, time is passing. What happens with your growth? It's just amazing. All right. First example, the average annual growth rate for world population since 1650 has been about 0.7%. So that's on the graph prior to the takeoff here. 0.7% growth is happening. It's unnoticeable really on the graph. However, the annual rate has varied significantly. It peaked at about 2.1% during the 1960s, and is currently, as of 2017, about 1.1%. So find the approximate doubling time for each of these growth rates and use each doubling time to predict world population in 2060 based on a 2017 population of 7.5 billion. All right, for that, we will go to our actual paper so that I can write out the problem here. So it's right here. And what we have is we have 3 times, and I'm just going to highlight it, 1650, and then 1960s, and then another time, let's see, and then 2017. All right, so I'm going to just make a little chart here because we're going to be working through several formulas. So we have 1650, 1960, and 2017. And in the year 1650, we had about 0.7% population growth. And then in 1960, 1.1%. And then 2017, we had, 2.1% is where it peaked in 1960. My bad. 2.1%, and then in 2017 was the 1.1%. I had to reread that again to get that. All right, so approximate. First of all, it says find the approximate doubling time. So as we know, the formula for that is 70 over p percent, and we leave it in the percent. So that's going to be 70 divided by 0.7, and then 70 divided by 2.1 for 1960, 70 divided by 1.1 for 2017. All right, and then in the calculator, if you place that in, again, I kind of like to do my calculations, we'll do 70 divide 0.7 is 100. Probably could have done that one. And then I'll just go up, hit it again, 2.1 is 33. It's 33.333, but we're just going to use a rounded integer. And then 70 divided by 1.1 is 64. So that is our doubling time. And I'm just going to write that just in case. That's approximate, of course. So that's one thing that we asked for. The next one says, use each doubling time to predict world population in 2060 based on a 2017 population of 7.5 billion. So that's going to be our initial population that we'll use in our formula. And if you recall, what we do is we take that amount, the initial population, and multiply it by the factor 2 to the time, divided by double time. Now, really quickly, what is t? Well, 60 minus 17 is how much time has passed since the initial population of 7.5 billion. So if we take 2060 and subtract 2017, we get 43 years. So little t is 43 years. So that means we're going to take 43 divided by our time, doubling time. In this case, it's 100 in 1650. And then in 1960, it's 33 years. So 43 divided by 33, because this is our doubling time, it goes on the bottom. 7.5 times 2 to the 43 over 64. All right, and that's going to be the population, the new population, after that much time has passed with the rates. And we know rates change over time. So in their calculator, if we put 7.5 times 2 to the 43 divided by 100, and then that is 10.1, and this is in billions. So 10.1 billion will be the new population. All right, if doubling time stayed 7% the whole time. Now, if it stays 1 point, what's next, 2.1? Now, if the growth rate stayed at the 1960s rate, 2.1%, we would have, I'm just going to go up and hit enter so I can just change the doubling time. I can get there, I'm paying attention. So 33 needs to be placed for the doubling time, and that's 18.5 billion. That would be our current population if the rate had stayed the same as it was in 1960. And then 2017's rate, 1.1, would be, I'm just going to extract it and type in 64 where 33 was, and that is 11.9 billion. All right, so that would be the actual rate that, or the actual population, the new population, based on rates that have happened over time. All right, so the next thing we're going to learn is overall growth rate. So let's go back to our PowerPoint. We did that one. Power through that. All right, overall growth rate. Now, we have to understand what that growth rate is in order to go through I don't know, all the statistics that we're learning and everything with this lesson. And out there we have a growth rate, and what it is the difference between the birth rate and the death rate. So in the last problem, when it was 1650 and our growth rate was 0.7%, that means if we took the birth rate and then the death rate and subtracted the death rate from the birth rate, then that would be our growth rate, and then they averaged it over time from time zero that they know of anyway to 1650. And they came up with 0.7%. So any given species in an environment, you have an amount of sustainable population, and we call it the carrying capacity. So that would be the largest population the environment can support for extended periods of time. So if I always think of when I would go to the pet store a long time ago when I had kids and they wanted to go buy a fish. And we'd head up to the pet store and we'd look at the different tanks with goldfish in them. And generally there were one or two little goldfish at the top of the tank that were floating on their sides and they were dead. And I always would think of carrying capacity in that way, that that tank had so many so much in order to sustain so many goldfish, but they exceeded that. The people at the pet store had exceeded that amount or that limit, had put more fish into the fish tank, and then it couldn't sustain the water, the food levels, or oxygen rates, whatever, wouldn't sustain that. And so a couple of them died over time until everything stabilized again. So that's carrying capacity, just in a little example of in the pet store. But the largest population of the environment can support for extended period of time is going to be our carrying capacity. You won't have any questions on that in the homework. That's just for your information that there is that out there in the wild. And birth rates, a lot of people are concerned with, well, what is the carrying capacity of the earth? And you hear that a lot, but I just wanted to point out here that birth rates have dropped rapidly throughout the world during the past 60 years, the same period that has seen the largest population growth in history. So birth rates have dropped. So if you take this part here, the birth rate, if those drop and we're still getting a very big increase in population, then that means what? That the death rate has dropped as well. And that means because of technology and increased healthcare and everything that we've learned over time, our people are living a longer time and they're not dying so quickly. And therefore, that's why we still have the largest population in growth in history, just because our death rates are smaller and our birth rates are smaller. So today's rapid population growth comes from the fact that death rates have fallen even more dramatically. So we have a little example here. In 1950, the world birth rate was 37 births per 100 people. And the world death rate was 19 deaths per 1,000 people. By 1975, the birth rate had fallen to 28 births per 1,000 people, and the death rate to 11 deaths per 1,000 people. Contrast the overall growth rates in 1950 and 1975. So we have 2 years here. I'm going to actually go to my paper again so I can write on it. All right, here we are. So in 1950, I think that was 1950, we had 37 births. So we're going to take 37 births per 1,000, and the death rate was 19 per 1,000. So that's our formula, our growth rate formula. We have the birth minus the death rates, and that is 18 over 1,000. And if you put that in the calculator, which I'm not going to, you just move the decimal 4 places, and or 3 places because you have 3 zeros. So 0.018 or 1.8% is what would happen in 1950. Now in 1975, we have 28 births and then 11 deaths per 1,000 people. And that is 17 over 1,000, which is 0.017 or 1.7%. So you would say that the overall growth rate barely changed because the death rates fell. Notice the death rates fell in each case just as much or almost as much as the growth rates fell. So we had a fall of 9 and we have a fall of 8, and between the 2 years that we're looking at, and that made our growth rates pretty much the same. They just barely dropped. All right, I'm going to stop this lesson so that I can do the last 2 here in a minute, and I can upload my video successfully. So stay tuned, do part 2 of 8B. Oh, C.